Hello, everybody, and welcome to your second lecture on ocean circulation. So we're continuing along looking at the different currents of the ocean. Here's this familiar image showing the famous Gulf Stream there. You can see it moving from the Gulf of Mexico, of course, into the Atlantic. Let me get my drawing pen up here. Okay, so this is you can see the Gulf Stream, very strong, very strong current, very important current historically. So we're continuing along learning about differences between western and eastern boundary currents. You could see your first question here on your lecture assignment. If you have your next lecture assignment here, right, should look like that. You have to draw a map of the different currents. So I should probably bring up, let's see if I have a map of all the different currents here. Oh, no, they're right in front of me, right? So there you are. You have to draw that. Draw that out, the six major gyres. The one gyre that isn't shown here is this, of course, one here in the Southern Ocean. That's going this way, the westward drift. So you have to draw on that gyre, of course. That's a little bit of a strange one, right? Because it's circumnavigating the whole world. So, but anyway, we're going to continue along. So you have to draw this, your first question on your lecture assignment. And also you need to label those western and eastern boundary currents, right? So here are your, of course, on the western side of the boundary of the gyre, those are your western boundary currents, and then on the eastern side are of course, the eastern boundary currents. Okay, there's some famous ones here. We're going to talk about a couple of them. There's the California current right here. There's the Canary current, the Benguela, the Humboldt, and the Western Australian current. Okay, so those are the five that you should know. So there's only five of these eastern boundary currents, even though there's six gyres, and it's because that westward drift gyre in the Southern Ocean is kind of different than the other ones, right? It's actually quite different than the other ones because it's going around the whole world instead of directing water towards the equator and away from the equator, et cetera, et cetera. Okay, so anyway, let's talk a little bit about these eastern boundary currents and kind of compare and contrast eastern boundary currents with western boundary currents. So you know that western boundary currents are really different in every way than eastern boundary currents. Okay, so when I say that eastern and western, what do I mean? I mean this eastern side of the gyre compared to the western side that's moving water either, in the northern hemisphere it's moving water from north to south towards the equator. In the southern hemisphere it's moving water from the south to the north. But always, you'll notice they're always moving water towards the equator. You see that? Eastern boundary currents are always moving water towards the equator. Western boundary currents are always moving it away. Now, because of that, you're going to get differences between eastern boundary currents. Just in their characteristics, we're going to get differences. So we're going to, number two, I ask, western boundary currents are deeper, faster, and narrower. Why? Why is that? And it has to do with that fact that, again, eastern boundary currents are moving water towards the equator, western boundary currents are moving away from the equator, and there's going to be a difference due to both geostrophic effects. If you remember what I meant by geostrophic, I'm going to discuss that in a bit. And then also the Coriolis effect causes it. And again, in this class I always say, if you don't know why something happens the way it happens, a good guess is always Coriolis effect. So Coriolis effect really affects a lot of things in the oceans. Okay, so eastern currents are carrying cool water towards the equator. The reason that it's cool is very simple. It's usually coming. It's always coming from a higher latitude, colder place to a lower latitude towards the equator, right? So you're always bringing cold water from higher latitudes to lower latitudes. So that's why it's colder. It always goes towards the equator. We already saw that. They tend to be wide, shallow, and they don't commonly have eddies spin off. The reason that they don't have these eddies spin off is just because they're moving more slowly. That's it. It's just that faster water is going to be, more typically, it's going to form eddies, okay? Now, we do need to talk about why they're wider and shallower, because that's something that's not, maybe not as intuitively clear. So we'll talk about that in a bit. Western currents are stronger. The Gulf Stream, right, is a western current. They have what's called western intensification, which I'll explain that in a bit. The Coriolis effect is, again, Coriolis effect arises from whenever you have any moving fluid, whether it's air or water. The Coriolis effect always causes a deflection in the global direction of the movement of that fluid. So whether it is water moving, and I'm not talking about things moving, over meters or even a kilometer. We're talking about things that are moving globally, things that are hundreds of kilometers they're moving. So that happens with air or water currents. They're going to have a deflection in their direction, either to the right in the northern hemisphere or to the left in the southern hemisphere, and it's due to the fact that the Earth is rotating, right? So, the Coriolis effect is stronger near the poles. It is weaker near the equator. So that's what is causing what's called the western intensification. You got a stronger western boundary current than you do an eastern boundary current. Okay, trade winds contribute to that western current as well. So we're going to talk about how all that plays out here. Okay, so without the Coriolis effect, gyres would look like this. Okay, they basically be perfect and symmetrical. Okay, they would just be rotating very nicely. However, because we have Coriolis effect, we get this kind of asymmetrical, non-symmetrical look to the gyres. Okay, so when the water is going along the equator and it turns to the right here, forming of course that forms the western boundary current. Notice that it is tighter, it's deeper. The water is moving kind of a narrower path and causes it to be faster, deeper, and more intense. Okay, now that's because we have right here a weaker Coriolis effect. And we have a weaker Coriolis effect because it's moving from the equator where the Coriolis effect is weaker, right? If you don't understand or don't remember why, you have to go back and listen to our lecture on air circulation, the previous lectures. But you have a weaker Coriolis effect near the equator. Now over here you have the western boundary current, and right here you have a greater Coriolis effect because the water's moving at a higher latitude. So remember, at higher latitudes, the closer you get to the poles, the more intense the Coriolis effect is. So you get a lot more water turning. It's turning over a larger area. So and the reason that's turning over that larger area is due to that stronger Coriolis effect. So the Coriolis effect is stronger, and because it's stronger, it's spread out over a larger area, and so you kind of get this. I guess you can say de-intensification. You get the current being spread out over a larger area, and therefore it ends up being shallower and slower, and yes, it's not as intense. Okay. Now another effect that's happening here. Let me erase the thing. It's not only that. It's also something called geostrophic effects. So let me explain a little bit about what I mean by geostrophic. So geostrophic. Remember that the trade winds are blowing in this direction, right? They're blowing along the equator. Now, when you have those trade winds blowing, it creates kind of a hill of water that's on the western side of the gyres. Okay, and because remember that constant blowing, prevailing winds of the trade winds build up the water and create kind of a hill of water that would exist right here. So what happens is you get this hill of water or mound of water that's built up on the western side of the gyre, and that ends up kind of pinching the current into a narrower stream. So that's another reason that you get the western intensification. Okay, so I just explained for almost 5 minutes, 5, 6, 7 minutes about the answer to number 2. Okay, and very simply, what you can put for number 2 is it's due to geostrophic effects and the stronger Coriolis effect that prevails at higher latitudes. maybe even very simply, you could just say it has to do with the Coriolis effect and the geostrophic effect from the trade winds. Okay, and that would be enough. I'm kind of fleshing out a lot more details, but it's enough for this class to just kind of chalk it up to that. So again, western currents, the western boundary currents and the eastern boundary currents. Currents from the west, they're bringing warm water from the equator up to higher latitudes. In the eastern boundary currents, they're bringing cold water down from higher latitudes near the equator. Western boundary currents have higher salinity. They have lower oxygen content, and they have lower oxygen content usually because they're warmer, right? Warmer water, generally speaking, has lower oxygen. Eastern boundary currents have lower salinity, but they have higher oxygen contents because they're colder. And the colder water brings a lot of oxygen. So nutrient upwelling in the western boundary currents is infrequent, and then it's nutrient poor, whereas nutrient rich due to upwelling. Okay, we'll talk about upwelling in a bit. So this western boundary currents have lower biomass, eastern boundary currents have higher biomass. So these eastern boundary currents that you see, I'm showing them here, they're very important for fisheries. This is bringing a lot of cold, oxygen-rich, nutrient-rich water into the area where it's starting to warm up. It's bringing it from the south, from the higher latitudes, I should say, nearer to the equator where it's warmer. It starts to warm up. It's got a lot of, and think about that. You got this water. It's full of nutrients. It's full of oxygen. It's starting to warm up now, and it's gonna be just great for fish and marine life. Okay, so these are really, really important currents for sustaining fisheries. The California current, very, very especially, I can say the California current and the Humboldt current, very important. This is, by the way, why we get. If I don't know if any of you have ever been to California or been to our west coast, you will notice that the ocean water on the west coast is a lot colder than what we get in the Gulf of Mexico. It's a lot colder. So, if you go there, you'll see a lot of surfers wearing wetsuits and things like that because it's cold water because of the California current. Okay. So we talked about all this stuff here. Now, boundary currents, the eastern and western boundary currents are connected together by what we call the transverse currents. So I already talked about number 3, explaining some differences between eastern and western boundary currents. There's a lot of things. Look at this. There's really a lot of things that you could say about them. You could talk about nutrient differences. You could talk about oxygen differences. You can talk about just geographically that, western boundary currents are moving water away from the equator up to higher latitudes. Eastern boundary currents are bringing cold water from high latitudes to lower latitudes towards the equator. There's so many things you could mention there. So now let's go on to number 4, is asking about transverse currents. Okay, what are transverse currents? Transverse currents are the currents that are connecting the western and eastern boundary currents together to complete the gyre. They are moving, rather than moving north to south or south to north, they are moving east to west or west to east, okay? So along the equator, they're always moving, you can see, from east to west, right? They're always moving in this direction. At these higher latitudes, they're always moving to the east, okay? So you'll see up here, they're moving to the east, right? So these are connected by the transverse currents. Okay, transverse currents are driven by the strong trade winds near the equator, right? And then driven by the westerlies at higher latitudes. Okay. So you'll notice this is a pretty good. This is what I was talking about, geostrophic effects. So take a look at this. This is a map that shows you the kind of the height of the ocean, the ocean's surface. Okay. Now remember, I told you that the ocean's surface is not perfectly level. There are hills and valleys. Now these hills and valleys, they are not. I can say they're not like big hills. We're talking about. You can see the maximum range of this is 160 centimeters plus or minus. So you're really only talking about 320 centimeter range. Okay, that's not very big. That's 3 meters. So it's about 10. You're talking about something that's about be like 10 feet. Okay, 10-foot range. So that's what I mean by the hills and the valleys. They're not big hills, but they're little hills, but they're there. Okay, they're not big valleys. They're little valleys, but they are there. Okay, so where is the water really high? The water's really high right here, right? Right here. You notice how on the western side, the water is always higher. You see that? See in the western side of this gyre, the western side of this gyre, it's higher than over here on the eastern side. It's higher. The western side is higher than on the eastern side of the gyre. The western side is higher than on the eastern side of the gyres. You see that? Why is that? It's due to the blowing of the trade winds here. So we get the trade winds blowing this direction, right, from west to east, or sorry, from east to west. That's going to build up water. It's going to make kind of like hills of water. You could imagine if you, had a basin of water and you had a hairdryer or whatever, a fan or something blowing water in one direction all the time, you're going to build up water on one side of the basin and you're going to have lower water level on the other side of the basin, okay? So that's what's going on. You have the trade winds blowing this direction. It's very strong winds, and you get this buildup of water kind of on the western side. Well, that creates what's called a geostrophic effect, okay? So the ocean surface elevations are higher on the west side of the oceans. It's due to the buildup from the trade winds and the westerlies, okay? So transverse currents, these are east to west or west to east currents driven by the trade winds or the westerlies, depends, the ones that are the near the equator driven by the trade winds, the ones that are higher latitude driven by the westerlies. These are the equatorial currents are moderately shallow and broad. They pile up water on the west side of the basin. The eastward flowing currents at mid-latitudes are weaker and wider than the equatorial currents. So the differences in landmass distribution, north and south hemisphere, affects flow, because you know that there's more landmass in the northern hemisphere than in the south. Okay. Let's also take a look at kind of this other weird gyre. You know that there's the Antarctic circumpolar current, the westward drift. It's the greatest of Earth's currents. Now, it is special because it is totally unimpeded by continents. And so it's just driven by the westerlies, and its flow is very strong. It's much stronger than the Gulf current, and it just goes unimpeded by continents, right? So this picture that you're looking at right here, you're looking at Antarctica, and you can see that basically the water just flows around and around and around Antarctica, driven by the westerlies, okay? So it's just a single transverse current, right? It doesn't have western or eastern boundaries. All right, so now let's talk a little bit about what it's like we've talked a lot about the boundary currents of the gyres, but I want to move on now to what it's like on the inside of the gyre. So if you go to the inside of the gyre, what do you have? You don't have a lot of water movement. You don't have a lot of water movement. So you have these relatively calm interiors. So one of the very famous seas in the world is called the Sargasso Sea. The Sargasso Sea. So what is Sargasso? Sargasso Sea is this area right in the middle of the gyre, right in the middle of the North Atlantic. So that's the Sargasso Sea. Okay, it's a very, very unusual place because it's absolutely filled with this floating seaweed. It's really actually an algae. It's a floating algae. Seaweed. Most seaweed is actually just algae called sargasso or sargassum. Okay, so it ends up, because it's floating, it's not tied down to the bottom of the ocean. It ends up just kind of collecting in the middle of this gyre, right? Because you get this circulation around the gyre, and it's almost like an eddy, and the floating stuff is just going to collect in the middle of the gyre. Unfortunately, this is also what happens now to like plastic trash in the ocean, right? It just accumulates in the ocean, and it floats, and it ends up just collecting in the middle of these gyres, right? So you have these big plastic islands, trash islands now. But besides that, there's also sargasso. So It's a really, really interesting ecosystem. I wish I could spend some time a little later in the class talking about Sargasso ecosystems because they're really interesting. Um, so hopefully we'll have a chance to get to that. All right, we're also going to talk about. We've spent a lot of time now talking about what we can say maybe horizontal movement of water, right? So water either going east or west or north or south. But of course, the oceans are three-dimensional, right? So you can go up and down as well. So now we're going to kind of switch gears and change and start talking about vertical movement of water. Okay, so let's talk a little bit about upwelling and downwelling, and that's downward or upward movement of water in the ocean. So you know that surface currents that we've been talking about before, like the western boundary currents or eastern boundary currents, the transverse currents, et cetera, those are driven by the wind, right? They're mostly driven by the wind. They're affected also by the Coriolis effect. They're affected also by geostrophic effects, which are ultimately due from the wind. But wind is a major factor in driving those surface currents. Okay. So wind is also responsible for some of the downwelling and upwelling and the vertical movement of water as well. So we'll talk a little bit about that. So upwelling is the vertical movement of colder, relatively dense water to the surface, and it occurs in areas where the horizontal currents diverge. Okay, it means where they separate and they come apart. Downwelling is the vertical flow of warm, less dense water towards the ocean bottom. This occurs in areas where horizontal currents converge or come together. Okay. So where you get convergence zones, you're going to get downwelling, and wherever you get divergence zones, you're going to get upwelling. So let's take a look at some of these things. So upwelling and downwelling occur in the open ocean, where winds can cause surface water to diverge and move away from a certain area. Upwelling takes place along much of the equator. So remember that when you go along the equator, you have the trade winds blowing along the equator, and they're going to turn to the right due to Coriolis effect in the northern hemisphere, and to the left in the southern hemisphere, and that creates diverging water. So as you get this blowing along the equator, you're going to get divergence, right? In the northern hemisphere, it's going to blow to the right. To the southern hemisphere, it's going to blow to the left, and you get divergence, and that's going to cause upwelling. So along the equator, you get upwelling. So I want to show you, this is a map showing where upwelling mostly occurs. And you can see that the strongest upwelling is occurring along the equator. This is very important because this is bringing cold, oxygen-rich water up to the surface. Okay, it's bringing cold, often nutrient-rich, oxygen-rich water up to the surface. So this is a wellspring of life for marine life in the ocean along the equator. Okay, upwelling is extremely important for marine life. Okay, so why is this happening? It's because the trade winds are blowing like this, right? They're blowing east to west, and they diverge. Okay, they diverge either to the right in the northern hemisphere, right? This is part of the gyres, right? It's part of the gyres. So you get this divergence because there's a rightward movement in the north or leftward movement of water in the south due to the Coriolis effect, and you end up getting diverging water and you get upwelling. Remember, whenever you get diverging water, you get upwelling. Whenever you get converging water, you get downwelling. Okay? Upwelling is bringing cold water from beneath, cold nutrient-rich water from beneath. That fish love that. The marine life love that. Downwelling is going to have the opposite effect. Okay, it's going to take warm, salty, nutrient-depleted water and push it down into the depths. Okay, upwelling is very important for ocean ecosystems because it's bringing nutrient-rich, deep water to the surface. So this is a map showing nitrate concentrations in the ocean. Nitrate is a very important nutrient for all plants, but also phytoplankton, anything that's using chlorophyll uses nitrate, needs nitrate to survive. So nitrate's very, very important. I know that we kind of think of nitrate as maybe like a nasty chemical for us, and for us it is, but for plants, phytoplankton and things like that, they need the nitrate. It's a very, very valuable, nutrient. You can see that nitrate is getting concentrated here in the equator due to upwelling. Okay, the reason that you don't see a lot of nitrate along the equator is because there's a lot of life in that warm water that's using it up. Okay, you see more nitrate concentrated in the colder areas, and that's simply because there's not as much phytoplankton to use up the nitrate. Okay, it's colder, there's not as much life. You know, if you go to Antarctica, there's not a lot of plant life, right? It's too cold to really sustain a lot of phytoplankton and a lot of photosynthetic life, so it tends to build up in those polar areas. That's why gyres are so important to bringing nutrient-rich waters into the south. Okay, or into the near the equator. So photosynthetic life like seaweed, algae, phytoplankton, they need nitrate, they need phosphorus. They also need potassium, but you might remember that potassium is very abundant in the ocean water, so it's not as important of a kind of like it's not as a problem, right, for seaweed and phytoplankton to find. Another thing that's very important is iron. So to grow and thrive, nitrate, phosphorus, and iron are very important because they're rather limited in the oceans. Remember that potassium is not like a limiting variable, right? There's a lot of potassium in the ocean, but nitrate, phosphorus, and iron are relatively rare. So plant life and seaweed, algae, phytoplankton are fighting for survival, and they're trying to get their hands on those nutrients. All right, so upwelling is typically occurring along coasts where the longshore wind blows parallel to the coast. So remember, Ekman transport deflects currents to the right, which causes upwelling. Okay, so if you can imagine, if the wind is blowing along the coast, okay, wind is blowing along the coast like that, you're going to get, remember how you have Ekman transport, right? You get Ekman transport, and that causes water movement always at right angles, perpendicular angles to the right of that wind. So you get the surface wind, and you get water currents blowing to the right like this, and that's going to cause a divergence in the water, right? So water's moving this way, it's moving off the coast, and as it moves off the coast, cold water from down below is brought in, and there's upwelling. So remember, whenever you get diverging water, you end up with upwelling, okay? So let me erase all the ink on the slide so you can see this better. So now, where you have the longshore wind that's blowing in the opposite direction, you can get downwelling, right? So same longshore wind can cause downwelling in a different set of circumstances. So it's kind of hard, you could talk about all the different circumstances, like if you have like an east coast or a west coast, and you have the northern hemisphere and the southern hemisphere, and then you have a southerly wind or a northerly wind. See, there's all these variables that come into play. But the basic pattern is, if the Ekman flow is going to be off the coast, you're going to get upwelling. If the Ekman flow is going to be down the coast, you're going to get, or towards the coast, you're going to get downwelling. Okay, so let's go West Coast. There we go. All right. So again, upwelling, you got to remember, upwelling of cold, deep water is so important for marine life. Cold water is normally richer in nitrate. It's richer in different nutrients, and it stimulates the growth of phytoplankton, which is the basis for the marine food chain. Okay, so downwelling is always good for fish, for marine life in general. Okay, upwelling is always good for marine life, whereas downwelling is going to have the opposite effect. Okay. Now I hope that looking at this, maybe this is a global map of chlorophyll concentration. So this is showing where there's a lot of plankton in the oceans, and hopefully it kind of makes a little bit more sense now. You get a lot of plankton. Of course, along the coasts, you're always going to get a lot more plankton along the coast. There's a lot more nutrients washing off of the continents. In the open ocean, you really only see plankton in the open ocean here along the equator, where you get strong upwelling, right? You can get it in along the currents, but you notice that on the insides of the gyres, there's very little phytoplankton. There's very little life. And the reason there's very little life is because there's so little circulation of water. So what happens in the gyres, on the inside of gyres, is that there's not much movement of water, not much circulation of water. So the surface water is depleted in nutrients and therefore depleted in phytoplankton and marine life. So there's not a lot of life and not a lot of action going on the inside of the gyres. There's these special areas that are called high nutrient, low chlorophyll regions. So it's called HNLC regions, high nutrient, low chlorophyll regions. Now that's a little bit interesting, right? Think about that for a minute. You have a lot of nutrients in the water, but you have low chlorophyll, which means a low degree of phytoplankton alive in that area. So the places where we get, for example, low chlorophyll concentrations, yet we have high nutrients. So if you take a look at, this is a map of phosphorus, things like that. This is a map of the HNLC zones in the ocean. See, why doesn't the phytoplankton use all the nutrients available here? So here, right here, we get relatively high nutrients but low phytoplankton levels. Now, some of these things you might be able to chalk up to the cold temperatures, that are lowering the amount of chlorophyll, amount of phytoplankton that can survive there. But some places here, we have high nutrients, like here near the equator, we have high nutrients, but very not sufficient amounts of chlorophyll, phytoplankton. You think that there would be more, should be more, given the nutrient levels there. So what are some of the reasons for that? Some people think, or some scientists think, this could be because there are other limiting nutrients that are not present, especially iron. Iron is a very, very important nutrient, and it's a very limited nutrient in the ocean water. Remember from our ocean water chemistry lectures, there's very, very little iron, just trace amounts of iron in the water. It gets used up very quickly by phytoplanktons, okay? So in places, you can notice that a lot of iron is actually brought to the ocean by wind-blown dust. And like in this part of the ocean, that was a HNLC, high nutrient, low chlorophyll part of the ocean. You'll notice that very little dust gets blown into that part. So some scientists have argued that that could account for HNLC area, different HNLC areas, is that they just don't get enough iron from wind-blown dust. Okay, so we talked about number 9, why nitrate is important. We talked about deep water being more nutrient-rich. Number 11 says, what does upwelling do for nitrate concentrations in the open ocean surface water? Upwelling brings and rejuvenates the surface water and brings in new nutrients, especially nitrate. Okay, under which conditions is there coastal upwelling? We talked about that. Just talked about number 13, HNLC zones, and some theories to explain HNLC zones. It has to do with the fact that there isn't sufficient iron being brought in by wind-blown dust into the oceans. Okay. All right. So we're going to go on now to talk about El Nino and La Nina effects. I'm going to skip this Langmuir circulation, so I don't even ask about it. But so let's talk a little bit about El Nino and La Nina effects. Okay, so El Nino, La Nina are deviations. You've probably heard of these terms before. So these are deviations. Like maybe you've heard like, oh, it's an El Nino year or it's a La Nina year. You want to kind of understand what that means. So El Nino is deviations from the normal atmospheric ocean circulation patterns. So especially in the Pacific Ocean. So it involves the lowering of the thermocline. So that means the thermocline is going to decrease in its intensity. And it ends up with higher sea surface temperatures. Okay, so that's called SST. We're going to use that term as we go forward in this discussion. So make sure you know that, SSTs, sea surface temperatures. And it results in hot, humid weather conditions. So this is basically what I can say about El Nino years. You might know that El Nino years, typically for us in Texas, we kind of don't get the effect as much as places like California. But here in Texas, we're going to get more rain. And that more rain is due to the high humidity that is that's being added to the atmosphere from a relatively hot Pacific Ocean. So we want to talk about why does the Pacific Ocean, the sea surface temperatures of the Pacific Ocean get hotter. And basically what happens, so this is showing monthly sea surface temperatures during normal conditions right here. So this is normal. Okay, so that's what normal looks like. You'll notice that there's this kind of cooler part right here. And that has to do with, of course, the eastern boundary current, bringing in the Humboldt current, in this case, bringing cold water. You get movement of water, right? You get the trade winds. You get the Ekman transport moving like this, right? That causes divergence of the water currents, and you end up with upwelling. Okay, you get upwelling. So part of the reason that we get relatively cold water here is due to upwelling. Okay, the upwelling is driven by the trade winds. If for some reason trade winds were to stop, we're going to end up with much hotter conditions on the sea surface temperatures because there's no upwelling. Remember that upwelling is driven by the trade winds along the equator. So you get El Nino conditions. So that's when you get a cessation of the trade winds. Sometimes you get a reversal of the trade winds, and it stops upwelling, and you get relatively cold, you get relatively hot sea surface temperatures. That adds a lot of humidity to the weather, to the atmosphere, causes wetter weather, basically. Okay. La Nina is just the opposite. Usually La Nina immediately follows El Nino. So look at this is December 1997. We get El Nino. La Nina follows 1998, right? So it comes right on the heels of El Nino. You get a very strong trade wind, and you get very strong upwelling, okay? And it cools down the sea surface temperatures of the Pacific, okay? A greater sea surface temperature has a lot of bad effects. For one thing, you don't get the same upwelling, so you don't get the same nutrient replenishment in the surface seawater. So you get kind of a collapse of the ecosystems because phytoplankton don't have the nutrients they need to sustain life in the photic zone of the ocean, the upper surface level of the ocean. It also can lead to harmful algal blooms that can release toxins and harm marine animals. So you get these masses of dead algae that can decompose, and they suck oxygen out of the water. And it can cause massive fish kills. So this is actually, what you're seeing here are not actually fish, but they're actually squid and cuttlefish, and just a tremendous number of them. These are off the coast of Chile during El Nino years. It can lead to just massive fish kills and a collapse of the marine ecosystems for a year. So they're very strong effects and bad effects on marine life. Also can cause kind of different sort of weather. For us, during an El Nino year in Texas, you're going to get kind of wetter weather from November to the following April. So California really got, when I lived in California, I grew up in California, we had an El Nino year, like I showed, in 1997. I remember that, actually. It was a really devastating El Nino year, and So yeah, things like this. This is actually from that time period, 1997, 1998. Lots of wet weather, lots of landslides. California kind of has a hard time handling when you get superabundance of rain, because there's a lot of hills that collapse, and a lot of landslides and mass movement. So things like that. This is just a very, very classic picture of California during that El Nino year. So anyway, I want to show you this little video. It just kind of explains El Nino in more detail.
Warmer or colder than average ocean temperatures in one part of the world can influence weather around the globe. Boggles the mind, right? Here's how it works. During normal conditions, trade winds, which blow from east to west, push warm surface waters towards Asia, piling it up in the western Pacific. In some years, though, the trade winds weaken. The warm surface water moves eastward and reduces upwelling of cold water off the coast of South America. Climatologists call this El Nino. Its climate impacts show up mostly in the wintertime over North America. The warmer ocean fuels an intensification and southward shift of the jet stream. This brings flooding to the southern United States and warmer, drier conditions over parts of the Pacific Northwest, northern U.S., and Canada. But eventually, those trade winds pick up again and sometimes become even stronger than normal. When that happens, they blow the warm water back into the western Pacific and restart the upwelling of cool water towards the surface in the eastern Pacific. These strong trade winds are a signature of what is called La Nina, unusually cold conditions in the tropical Pacific that displace the jet stream northward. La Nina can lead to drought in the southern U.S. and cooler temperatures, heavy rains, and flooding in the Pacific Northwest. El Nino and La Nina together are part of a cycle that influences extreme weather and can impact food production, water supply, and even human health, not just in the U.S., but in many parts of the globe.
Okay, so there you have it. So there's a temperature map, shows the birth and death of El Nino. So you can see that the temperature anomalies, these are kind of like higher than average temperatures there on the western side. But then you'll see it slowly changing. It becomes cooler than average right here, June 2016. So that would be a La Nina year, okay? And then you get a return to kind of fairly normal conditions, okay? So you can hopefully get a clear idea of it from there. All right, so besides, so far what we've talked about is all wind-driven stuff. Everything we've talked about so far is all ultimately wind-driven stuff, or stuff that's maybe kind of currents that are affected maybe by not just wind, but also Coriolis effect, geostrophic effects, things like that. But I want to turn now and end with a little discussion of deep ocean currents, which are not affected by wind. Okay, so in the deep water, things are different because you're not having really any effect of wind, right? Because wind is a surface phenomenon. So we can get, everything we've talked about so far is surface circulation, which is really only 10% of the ocean. Okay, most of the ocean is deep water, and there are deep water currents as well. Now, deep water currents are not going to be driven by winds, right? They're going to be driven by density differences. So deep water ocean currents, thermohaline currents, are driven by density differences. We call them thermohaline currents because thermo, heat, so temperature, and haline means saline, means salt, salinity. Those are going to be the things that change the density of the water and cause there to be heavier or less dense or more dense water, and causes there to be vertical movement of the water. So one thing I wanted to remind you about, I'm not going to talk about like all of the different, just like there are all these different, surface currents, like the Humboldt current, the California current, et cetera, et cetera, et cetera. There's all these different thermohaline currents. I'm not going to talk about all of them. I only want to kind of focus in on one current, and just to kind of be like a case study to kind of get you familiar with the the sort of the principles that are at work here with thermohaline currents. So let's talk a little bit about what goes on in the Arctic. Okay, so you might remember that ice formation in the Arctic leads to saltier water. Now that salty water is going to automatically sink at polar latitudes, like in the Arctic, because there's no thermocline. Remember that? There's no thermocline at the Arctic. So as soon as the water becomes saltier due to ice formation in the winter, it's just going to sink. So what ends up happening is that you get this dense, salty water that during the winter is just going to start to sink, and that's called a thermohaline current. Okay, so we have different water masses. We call them central, intermediate, deep, and bottom waters. So I wanted to talk a little bit about some of the unusual characteristics of Antarctic bottom water, because it's kind of interesting. So if you imagine, every winter, if you get this sinking, salty water, what's going to happen is that you're going to get this sinking of the very salty water in the Arctic and Antarctic, and it's going to lead to the formation of a hypersaline bottom water. So one thing that's very unusual about Antarctic bottom water is that it is very, very salty. It's hypersaline. Okay. So I'm going to scoop over some of this stuff. I did want to talk a little bit about this. So this is a temperature salinity diagram. And what you see on the vertical axis, and you have one of these you see on your lecture assignment, so I want to show you how you do this. So you have temperature on the vertical axis, you have salinity on the horizontal axis. Okay. Now, this is kind of showing where different waters fall, and you see that the Antarctic bottom water is very cold, but it's also so I guess actually in this case it's not relatively saline. Antarctic bottom water. Okay, it's right here. So this water can be dense because of salinity or temperature. So these kind of diagrams are a common way to depict density as a function of both salinity and temperature. So these isobars that you see right here, these parallel contour lines, I shouldn't call them isobars, they're lines of equal density. So one thing that is kind of interesting I wanted to talk about is that you can actually get a mixing of two different kinds of water and produce something that is denser. Okay, so I want to show you how that goes. So you're going to have to do this on your lecture assignment number 20. So I want to see if I can get a blank one of these, but I don't think I have a blank one. So this is actually just showing this line. This red line is showing the typical changes in both temperature and salinity as you move down through the water column. But I wanted you to imagine something. Let's say that we took water. This is kind of interesting. You can actually take two waters of the same density, mix them together, and end up with something denser. So let's say I have one water that's here, and I'm going to call it water A. And I have another water over here, water B. Okay. Now they're along the same contour line, so they have the same density of 1.0285. Okay. So hopefully you see that. Now when they mix, they're going to mix along a straight line path from there to there. Okay. They're gonna mix along a straight line path. So notice that it doesn't follow the contour line. It's a straight line path between A and B. And if it's a perfect one-to-one mixture of A and B, a 50-50 mixture, you're going to get a density that's actually in the middle like that. So your density is actually going to be a little bit higher, closer to 1.0290 than the waters that you start off with. So it's showing you, what I'm trying to show you here is that you can actually, through mixing of waters, you can actually produce thermohaline currents. You can produce, different mixing of waters with different salinities and different temperatures. You can produce a denser water that ends up sinking. Okay, so you can get a sinking downwelling current just by mixing waters of different temperatures and salinities. Okay, so thermohaline currents are an important part of heat transfer along Earth. Water is usually sinking at the Arctic due to ice formation, and then it's sinking to a very low level, very deep in the ocean, and it moves along the ocean floor, and it upwells later along the equator. So you get these deep water currents that way, and it's very important for, again, heat transfer, and very important for nutrient transfer as well. Okay, so again, believe it or not, you can take two water masses of the same density but different salinities, different temperatures, and mix them together. That process is called caballing. And you can, A and B, right? And you make a tie line between them, right? And they mix to produce C. And you'll notice that water C has a higher density than either water A or B. Okay, so it's now denser than A and B. So Antarctic bottom water, like I said, is hypersaline. It's saturated at 34%. There's no thermocline at the poles, so that salty water just sinks as the ice forms. Okay, so I think that's all I really wanted to say. That's all I really wanted to say about thermohaline currents. I think I covered everything that's on your lecture assignments, so I'll stop there. And that's all there is for today. So I'll catch you next time, the next lecture, and we're going to think after this we're going to start waves and things like that. So I think the next lecture is on waves. So anyway, I will see you next time. Thank you for listening.